Geti makes it easier for people without AI expertise to create powerful AI solutions. How does AI training work? We choose the computer vision task to perform. We have our data annotated. Now we would like to train a deep learning model to perform this specific task on our specific data. I have no intention to make you an AI expert in 5 minutes, but I think it is important to understand few concepts before we begin. So in this short video, I'll explain how deep learning works and what is fine-tuning. In the next video, we'll talk about how to choose the right model, and the video after, I'll show you all the knobs and everything you need to know in order to train a model using Geti. The main conceptual change in our approach that made artificial intelligence what it is today is that we stopped programming. We stopped telling computers what to do. We stopped programming and we moved to teach them from examples. I'll start with what we call today traditional computer vision and explain how deep learning AI works. As you probably know, image is a large array of very small pixels. They are small enough for us to see a smooth image. Each pixel has a color value, which is usually a combination of 3 values for RGB, red, green, and blue. If we zoom in into this rectangle, we see the color intensity values of each of the pixels in the image. This is how computers see the image. If we look carefully, we can detect the edge of the snowboard where the pixel values drop at once. If we take a bunch of pixels like this and decide that each pixel will be the average of its surrounding pixel, and we do that for all the pixels in the image, each pixel will become the average of its surrounding. What will happen? The image will be blurred because the intensity level of all the pixels will be smoothened. If we take this window of pixels, but instead of averaging, we will increase the difference between the surrounding pixels, we will sharpen the image. And if we do it again and again and just keep the places where the differences between pixels is large enough, we will get all the edges in the image. And if we apply some threshold and keep only the most distinct edges, objects are starting to show up in the image. And we can see the features in the image, corners, lines, circles, and so on. When you look at an image, there are vast areas you don't care about. Your eyes focuses on very specific features in the image that really defines it. So, if I'd like to build a system that can detect cats, I need to find an object with 4 legs, which are parallel lines, a tail, and so on. This is our cat detector. Input image has to be multiply the values of each of the pixels, and the output will indicate if it's a cat or not. We will build a feature detector that can detect if an object has 4 legs. Another one will detect if there is a tail in the image. A detector to decide the color of the object, the size, and so on. Basically, we're getting in an input image, extract the features, multiply each feature by a weight. Feature 1 is multiplied by W1, feature 2 by W2, and so on. The results of this multiplication, the output, should be 1 if it's a cat or 0 if it is not. And let's train the model. We take a cat, multiply, and it's working. We got 1 at the output. This is a cat, and our function is working. This is also a cat, but the color is totally different, so it's not detected. So we need to adjust the weight of this feature. We need to change W3 so that the previous cat and this cat will both be detected as cats. And this object has also 4 legs. We need to change W1. And this object also has a tail. So we need a much more complex function if we want to be able to detect all of these cats and not to detect rats, tables, and others. And these functions needs also to have some nonlinearities, so we build a much more complex function. As you can see, it is built in layers. This is inspired by the structure of our brain, and each node here represents a neuron. We can have many layers, The internal ones are called hidden layers, and this is why it's called deep learning. The network is deep. And the truth is that these feature extractors are also just mathematical operations done on the image. So we can just take these functions and add them to our main function, and we have a one big happy neural network. Now we need to make sure it can really detect as many cats as possible. So we take a data set of many different cats. For each one of them, we will do forward pass. Basically, it means that we take the image and multiply it by the network, or apply the function of the network to see if the answer is really a cat, and we see if there is an error. Then we move backward, meaning we are changing the weights in order to minimize the error. During this procedure, again and again, is called training. The forward pass is called inference. Training these models could be a very heavy operation. It requires sometimes millions of images, very strong machines, and a lot of time. Modern models have billions of parameters, basically the weights we talked about and the biases. Recalculating these billions of numbers is a very computer-demanding task, but here is a question. Can we use the same neural network that was trained to detect cats with minor changes, make it detect dogs? Two techniques that we could use. The first one is fine-tuning. Fine-tuning means that we do not retrain the whole model from scratch. We keep the weights and biases of the model, we keep the original function, and we just introduce some new specific data to improve the accuracy of the model for our specific dataset. The second technique is called transfer learning. Please remember that the first layers are here to detect features, and a dog has almost similar features to a cat. It also has 4 legs, a tail, and so on. So what we can do is freeze most of the features of the neural network and use them as is, and only train the last layers so they could use these features to detect dogs and not cat. Geti is using fine-tuning. This is why it takes very little time to train such a complex model. It does not train it from scratch. The starting point is ready, converged model, and we're only fine-tuning it, just making small changes using very small numbers of new images. But which model to choose, and how do they differ from each other? See you in the next video.